Okay, thank you all for coming, and thanks a lot to the organizers. It's really nice to hear all these talks in honor of Raghu, and I personally have never met Raghu. When I was a grad student, my advisor, Amir, would take his sabbatical in the fall, sometimes at Courant, so then all of his PhD students would travel to New York, and we would each go for one time to visit him. And I was not really brave enough to talk to anyone other than Amir when I visited. And I think one time he forced me to go talk to Gerard, and I was barely brave enough to enter Gerard's office. And no one even thought to suggest that I would talk to Raghu, because everyone knew I would not dare to do that. So we have not actually met yet, but I wish you a happy birthday and many happy returns. This is a joint work with Bryce and Mark. We're both here, and
without the bow tie, right?
Say again.
Without the bow tie.
Without the bow tie, but you can still recognize him, I think. So, it has been a really great honor to be Bryce's advisor, and he's going to be on the job market this fall. So the talk is organized like the following. I am going to introduce the problem, and I'll give like some informal statement of the main result. It's in terms of an SDE, and there are maybe a bunch of different cases in increasing generality. So I will, and then most of the talk I will like try to present some ideas for a simple case of this SDE, and then tell you a little bit about the more general versions. So let me start with the problem that we're interested in, and this is a classical problem introduced by Diaconis and Friedman called projection pursuit. So imagine that you're in high dimensions and you have a cloud of points, and maybe this is some like high dimensional data that you have. And then the question they asked was, what possible low dimensions might you be able to see? And the idea was like, okay, you have a cloud of points, and maybe you want to be able to visualize it. So ideally, you would be able to choose some like nice two-dimensional direction in this high dimensions, and maybe it looks very like very informative in the two dimensions. So that was sort of the question. And then, so I'll use the same notation throughout, so I'll just introduce it now. So I'll collect the points in this m by n matrix. So there are m points, that's the number of rows, and they live in n dimensions. So we have m points and n dimensions, and then I'll just talk about one-dimensional projections in this talk. So U is the one-dimensional direction that I'm going to project on. And then the formal statement of this question is, suppose I'm given this m by n matrix, and let's consider the case that I just have a random matrix, IID Gaussian entries. And then if I take U to be a unit vector in the n-1 dimensional sphere, then what are the possible empirical distributions that I can see of all of the inner products of the rows with U? And I will also use this notation throughout. So I will just write law of GU for meaning I take this m by n matrix G, I multiply it on the right by this unit vector, so I get the one-dimensional projection in the direction U. And so then I will have m different scalar values. And this law of GU just means the empirical distribution of these m scalar values. And we'd like to know what are the possible measures that you can see. And it was proved by Diaconis and Friedman that if m is diverging relative to n, then all low-dimensional projections just look Gaussian, so regardless of what you choose for U. But it is known that in the proportional regime, where m and n scale in the same rate, then it is possible to find non-Gaussian projections, even if the typical projection obviously does look Gaussian. And it's not fully understood what is the set of all possible measures that you can see. So this is the projection pursuit question. And then I want to mention a closely related question, which is the perceptron from the title. And the perceptron in the most basic version is I take either the discrete cube or the sphere in high dimensions, and I intersect it with a bunch of random half spaces. So here it's drawn in 2 dimensions, but take the discrete cube on the left side or take the sphere and just put down a bunch of random half spaces, so pointing in random directions, let's say Gaussian directions. And the question is just what does it look like if you are in high dimensions and you intersect with a bunch of random sets? What is the nature of the random set that remains? And then in more formal notation, again, we can collect this in an n by n matrix with ID Gaussian entries. And then we ask, so the random set is just the set of x in either the discrete cube or the sphere, such that the inner product of x with every single row of the matrix, rescaled appropriately, is bigger than or equal to kappa, let's say, for kappa, which is a parameter of the problem. And if you take kappa equals 0, then that's this picture where all the half spaces are going through the origin. And if you take kappa large, then they're like offset from the origin in some direction. And then a basic question that you can ask in this model is, for example, for what values of alpha is this random set non-empty? So can you actually find any x such that this constraint will be satisfied for all of the rows? And this can be viewed, obviously, as a special case of the projection pursuit problem, because it's just saying, going back to projection pursuit, it's saying, can I find a U such that this empirical measure is fully supported on points that are to the right of kappa? Okay, so this is the perceptron model. And then just a couple of short motivations about the perceptron. So it's related to a bunch of other problems of interest. And maybe in interest of time, I will skip over this. So it's related to some toy model of a single layer neural network. And it's also related to some problems about discrepancy minimization for random matrices. And then, so just to say a little that the perceptron is also not so well, or has not been so well understood. So you can ask a lot of basic questions about what is the typical size of the set, what is the typical structure of the set. There have been a lot of recent works on this problem. And so one basic question is, is the set empty or non-empty? And it was conjectured in the physics literature that there's a critical ratio of m over n, where the set will go from non-empty with high probability to empty with high probability. And this one, there has been some recent progress, and I'll highlight this very recent paper of Bryce from this year. But this is not what this talk is about. So this talk is about what you can do algorithmically. So not about existence questions, but about what can you do efficiently. So then the way the problem is formulated is, given the matrix G as your input, we are asking for an algorithm which will output either an element of the sphere or an element of the cube, depending on your problem setting. And I want to do algorithmically one of these tasks. So the first task I mentioned is projection pursuit. So maybe you give me a target measure on the real line that you would like to see. So maybe some non-Gaussian measure. And the question is, can you find x, either in the sphere or in the cube, such that the empirical distribution of the projection in the direction x will resemble the target measure, let's say in like Wasserstein distance. And then, so this is maybe the most general version of the problem, and then you can ask for special cases. So let's say I'm given G as an input, and also I'm told a target interval in the real line. can you find X such that all of the rescaled inner products will lie in that interval? And then another variant of this is, let's say I'm given this function phi, which is called the activation function of the model. And I use this function phi to define this sort of Hamiltonian, which is just the sum of phi evaluated on all of the inner products. Can you find X to optimize this Hamiltonian, or to approximately optimize this Hamiltonian? So these are three versions of the algorithmic problem, and I will focus on the first one since it's the sort of the most general one. And yeah, so again, we consider both the discrete cube or the sphere. So maybe I'll say sort of informally what the result is. So for any given constraint density, a ratio of m over n, we can characterize what is the set of all of these measures. So what is the type of one-dimensional projections that you can see? We characterize a set of all such measures that are achievable by a broad class of algorithms. And again, the algorithm takes a g as an input and is supposed to output the direction x. And again, for both the sphere and the discrete cube. And some connection to recent work. So in the case of the sphere, the optimal algorithms were obtained in independent work of Andrea Montanari and Kanjie Zhou. And so our work gives the matching hardness bound in that case. And as I mentioned before, so I stated this in terms of the projection pursuit, but it also gives results for the constraint satisfaction and the optimization settings. Just to mention, there have been a lot of recent algorithmic results on the perceptron problem. So maybe I'll just highlight a couple. So there's a work of Ahmed Al-Alawi and Mark Selke that gives an algorithm for the negative spherical perceptron. And then there have also been some recent works that also give algorithms and as well as some hardness bounds for the Ising perceptron in both the symmetric and asymmetric cases. And I'll say a little bit more about these towards the end of the talk if I have time. But maybe some features that I can say in common that came from some of these works is that for in several settings, it's notable that algorithms were found to succeed even though typical solutions of the perceptron are isolated in many cases. So for example, if I take the Ising perceptron, then at any positive constraint density, most of the solutions are isolated, although it's also known that algorithms do succeed in that regime. And then, so since this is somewhat mysterious, physicists suggested that maybe one explanation for it is that algorithms are finding kind of solutions that are quite rare, but that live in dense clusters, so they're somehow more accessible by algorithms in the cube. And then there have been some fairly recent works that support this physics picture as well. Okay, so now I'll go to a more formal statement of the main result. So just to restate the problem, I am given this n by n matrix, ID Gaussian entries, and I want to consider the projection of it in the direction u. So I get m scalar values, and I want to know what is the distribution look like if I choose this u in an algorithmic way. And then the result is going to be a sharp algorithmic threshold for all algorithms that satisfy the following. So they have to be Lipschitz in the Gaussian disorder. So if I have two inputs that differ by a little bit, then the outputs can only differ by this much. This includes many standard algorithms. So it includes gradient descent, Langevin, approximate message passing run for a constant number of iterates. And but it does not include sum of squares methods, and it doesn't include the low degree polynomial framework. So I said it's a sharp algorithmic threshold, so that means that there is an algorithm side and a hardness side. So the algorithms are based on this incremental approximate message passing framework that was introduced by Montanari, and I'll talk a little bit about later. And then the hardness, which I will spend most of the talk on, it's based on this branching OGP framework that was introduced by Mark and Bryce. Okay, so this is a more precise statement of the result, which is that for Lipschitz algorithms, from the disorder to the output, the set of all one-dimensional projections that you can achieve, it's characterized by an explicit stochastic control problem. And we have a different stochastic control problem depending on whether it's the sphere or the discrete cube. And I will show the SDE in the coming slides for the various problem settings. So it's simpler for the sphere than for the cube. And it's also simpler if you add a symmetry assumption. So I will show the simplest SDE first and then progressively show the more complicated ones. And then additionally, we show that Lipschitz algorithms, they find dense ultrametric trees of solution clusters. Okay, so let me give the SDE in the simplest setting that we have, which is we take the spherical perceptron. And let's say that instead of caring about all of the inner products, we only care about the absolute values. And then I claim that this question is described by the following one-dimensional controlled SDE, which is that I have an SDE started from initial position 0. Sigma t is a progressive coefficient. And then the SDE is just dxt is sigma t dbt, so there's no drift. Subject to that for all time, it's run between 0 and 1. The expected value of sigma t minus 1 quantity squared is upper bounded by 1 over alpha. So I will try to explain in a moment where the SDE comes from, but at least as written, this is a well-defined problem. And then the theorem is the following. In the case of the spherical perceptron, if we only care about the absolute values of these inner products, then the set of these empirical measures that are achievable by Lipschitz algorithms, and I mean achievable approximately, they are exactly of the form, the law of absolute value of x1, where x is the solution to this one-dimensional SDE. Okay, so.
Why do you call that an SDE?
Sorry.
Why do you call that an SDE? You're saying x is a stochastic integral and you have constraint on the integrand, but they're not related sigma t to xt, right?
So sigma t will be a function of x.
Yeah, but at this point,
I mean, sigma t will be a function of x, so does that, yeah, is that okay? Okay. Okay, and then maybe just to have a picture of what this is saying, this is just repeating the SDE from before, and maybe this audience, I don't need this picture, but I guess we think of it as by default, you would take sigma t equals to 1. So in that case, the budget is always satisfied. So then by default, xt just evolves like standard Brownian motion. But because of this budget constraint, you can actually modify things a little bit. So you can change the local diffusivity as long as you satisfy this constraint. And it's of course easier to satisfy if alpha is small. So for example, in this picture, let's say mu t, this is the distribution of x at time t. And for example, maybe I make sigma t to be very large in the middle, and I make it to be small on the sides, as long as I satisfy this overall constraint. Then if you run it forward for some time, this might be what it looks like at time t plus 1. So this is the picture that we have in mind. And maybe also this is an obvious point, but the description is in terms of an SDE, but obviously the resulting evolution of the measure mu t, which is the law of xt, this is a deterministic evolution. Okay, so this was the theorem for the symmetric case, and then let me say quickly what is the general theorem for the spherical perceptron still. But no longer assuming that we have symmetry. So here it's again a one-dimensional controlled SDE, but there are a few more things that you get to choose. So there's a drift term, there's a variance term, and they're all subject to this budget constraint. And then P is this increasing differentiable function. And if I take P equals to 1, it recovers the symmetric case that I just presented. But this is, in general, a more complicated situation. And I'll try to say also where this comes from. And then the general theorem for the spherical perceptron is just that the measures of the inner products that are achievable by Lipschitz algorithms, they're exactly of the form distribution of x1, where x solves this more general SDE. Yeah, that's right. Yeah, exactly. And then, so this finishes the statement for the spherical case, and then we have an analogous result for the Ising case, which I think I should skip. But essentially, it's a system of two SDs that are coupled with one another. Okay, so let me say, I want to say a bit where the SD comes from and what are some of the proof ideas. So this is just restating that we want to understand this empirical measure of inner products. And so the proof idea has like these basic ingredients. So first, consider matrix Brownian motion G of t, which is conditioned to end at the input disorder. So your input is, again, this n by n matrix, and I consider an n by n matrix valued Brownian motion that ends at this G. And then the main object is this dupe martingale. So xt is the expectation of the algorithm's output conditioned on how much has been revealed up to time t. So it should be something that starts somewhere in the middle and then gradually travels to the surface of the sphere or to the discrete cube. And then the final position, x1, will just be the actual output of the algorithm. So this is a dupe martingale in Rn. And this is sort of the key object of study. Okay, so this is just repeating that. And then the point of this SDE is that it's to describe the evolution of this object. So we are interested in the empirical distribution of G times X rescaled. And so then consider GT, which is the Brownian motion at time t, multiplied with the dupe martingale at time t. And this is something that should evolve over time. It starts at 0 because G0 is 0. And then what we're going to argue is that mu t is the law of xt, where xt is exactly the solution to the SDE that we wrote down. So this is the interpretation of what the SDE means. And therefore, the mu1, the law of x1, it corresponds exactly to the algorithmically achievable measures. So this is the main like proof overview. Are there any questions at this point? Okay. And then maybe it would also be a good time for me to mention that so this dupe martingale, as I said, it travels sort of from the center to the surface. And because of Lipschitz concentration, because I have a Lipschitz algorithm, it has orthogonal increments. And this matches the known behavior of well-known spin glass algorithms. So it matches the behavior of algorithms of Suvag and Montanari, which are believed to be optimal or known to be optimal under some conditions. And at the same time, it also matches the intuition of this branching overlap gap framework that was developed by Bryce and Mark. So this is maybe sort of the reason why you would expect this to give the optimal thing. Okay, so let me say a bit about how to connect this to an SDE. So again, we have this Brownian motion, GT, the matrix Brownian motion, and the Doob-Martingale XT, and I want to track the evolution of this thing. So GT times XT, I get a vector of length m. So these are just the m entries of the m entries of this vector, and I just put them on the number line. And then I want to run time forward a little bit and have an understanding of how the distribution changes over this time. And the idea for trying to relate this to an SD is just take what you have at time t and discretize the space into these buckets. So the idea is that you would have like a large constant number of buckets, and each one is a small section of the space. And then run time forward a little bit, and in each bucket, the three particles in this bucket, they move to new positions. So you can get some local drift by just taking the average of the new positions that they move to, so that the average of the jumps. And you can also get some local variance by just taking the empirical variance of the jumps that they went to. So then this discretization gives you some way to write down like a local drift and a local variance. And then the hope is to relate that to an SDE. And then the caution here is that because of this bucket discretization, the ending description that we get, it's not really a pathwise description. So because we take like the bucket drift and the bucket variance, ultimately we are matching things in terms of one-dimensional marginals, but we don't have a pathwise matching. But this is the idea for relating this evolution to an SDE. And then, so let me try to explain in the simplest possible case where the SDE comes from. So for the spherical perceptron, let's consider the symmetric case. So in this case, it's enough to do something a little bit simpler. So instead of tracking the evolution of GT times XT, you can just track G times XT. And the idea is that kind of the optimal thing is for you to have all of G, essentially all of G revealed to you first, and then XT just moves at the very end. So essentially this XT is like a time reparametrization of like the movement that happens at the very end, and the G is like has been mostly revealed to you. But you can also just take this on faith that this is enough to track. And so then we have, again, all of these spatial buckets, B. And for each spatial bucket, as I said, you're going to define the bucket drift, which is the average of where all the sizes of the particle jumps, and then the bucket variance, which is the average of the squared bucket jumps. So it turns out that the drift is, in this case, is pretty close to zero just by concentration. But the variance can be non-trivial. And what can we say about the variance? So if we look at this thing here, it's so 1 over bucket size, sum over indices in the bucket, the vector indexed by that, dot product with the increment squared. So this should be upper bounded by the operator norm of this Wishart matrix, which is the sum of the outer product of the GAs. Okay, so then if I have a lot of different buckets, this is kind of complicated because I get a single delta xt that I get to choose. But if I look at the absolute simplest case that I have just one bucket, so let's say coincidentally everything at time t happened to be in a single bucket, then this is very easy, right? This is just a Wishart matrix where you, so it's the top singular value of a n by n matrix. So this is given by the Marchenko-Pastur law. And if you rearrange the extreme size of the Marchenko-Pastur, then you get exactly this constraint. And this is equivalent to our budget constraint in the case of a single bucket. But as I said, in general, you have multiple buckets, and they're all connected with each other because you get this single vector to choose. But in this case, you can, so you have some large constant number of buckets, and you can consider taking linear combinations of all of these and then use free probability to get what is the optimal value. And you can do this for any linear combination, so it gives you a bunch of constraints on what these quantities can be. And then if you take all of the intersection of all of the linear constraints, you end up exactly with the budget constraint as stated. So in the case of the symmetric spherical perceptron with many buckets, you can use this free probability calculation to eventually back out this constraint. Okay, so then this hopefully explains roughly how this is derived. So for the spherical perceptron, again, if you only care about the symmetric case, then the set of measures that are achievable by Lipschitz algorithms, they're exactly of the form law of absolute value of x1, where x1 satisfies this SDE. And again, this thing comes essentially from the Marchenko-Pastur distribution and from generalization if you take like a multi-scale Wishart matrix. And the last few slides were to explain how this is proved. And then maybe I should say, like, going from the discretization to the limiting SDE is complicated, maybe especially for those of us who are not SDE experts. Maybe Mark and Bryce are more SDE experts than I am. But most of it is using fairly basic techniques. So we have like moment estimates to show that the discrete processes go to some limiting semi-martingale. And then the main part is that if you have a semi-martingale that is nice enough, and you can write down its like occupation density and the occupation of its drift and quadratic variation, and it's possible to read off SDE coefficients from that. And then there's, for example, this paper that also surveys some methods that we used. Okay, so this is for the symmetric case. How much time do I have left? 7 minutes. Okay, great. So for the general case, it's more complicated because we need to track gt times xt rather than just g times xt. So then there are more terms that show up when you take an increment. And then, so there are more things to keep track of because the terms can be correlated with one another. But as before, this is handled with some sort of free probability calculation. So then this gives the more general statement for the spherical perceptron without assuming symmetry. And so one thing that I kind of hid in this is what is the role of this function p. So I want to say a little bit about that. So p is the inverse of this function chi, where chi is like essentially the squared radius that you are reaching at time t in the algorithm. So chi is like how fast your algorithm moves from the center to the outside. And we call it the radius schedule of the algorithm. So It's a little hidden because I didn't write down exactly what are the quantities that are showing up, but maybe going back to here, it's probably not hard to see that when you do this, it's an important input to the resulting PD will be just how large these quantities are, and this is kept track of by the P function. And then, as I said before, so if we consider only the symmetric case, then it's kind of enough to take chi essentially equal to 0, meaning that you stay near the origin and then do all of the movement at the end, which corresponds to the P function being close to 1. In interest of time, I will skip the Ising perceptron entirely. It's similar, but a little more complicated. And then I'll say a little bit about algorithms. So AMP is a class of first-order algorithms that have roughly the following form. So they act iteratively on. So you have some initial vectors, and then you sort of pass them back and forth using the matrix G. And the limiting behavior of such algorithms is pretty well understood. And the IAMP was introduced by Montanari and has been further developed since then. And in particular, the one from this paper, it simulates our SDE in the case that P is close to 1. And then we develop a new IAMP that simulates the SDE for general P, which is needed for the asymmetric setting. And then, so just to mention some applications, so these are for specific models of the constraint satisfaction problem. So this is like I do a projection pursuit, but you tell me the interval that you want all of the things to be in. And this is considering the interval can be like minus kappa to kappa, or the complement of minus kappa to kappa, or like kappa to infinity, or when kappa is large, or kappa to infinity when kappa is large and negative. So all the variants of this that you would consider. And there have been a lot of works on both the satisfiability threshold and the algorithmic threshold for such models. And for example, like in the symmetric Ising perceptron, the satisfiability threshold is up here, but the algorithmic threshold is all the way down here. Okay, so then, so this slide is to say that the SDE can be explicitly analyzed in some cases. And when I say it can be explicitly analyzed, I mean that Mark and Bryce can analyze them. So it can be analyzed by them to produce these algorithmic thresholds. So these top two boxes are for the symmetric settings, where either you're trying to stay in a small interval, or stay in a very large interval, or avoid a small interval, avoid a large interval, or these are the one-sided settings where you want to be in kappa to infinity, where kappa is either large or kappa is very negative. And this result in the Ising setting closes a gap between these two papers. And this result in the asymmetric setting closes a gap in this recent work. Okay, so I'm probably about out of time. Yeah, so I'll conclude. So the main result is a sharp characterization via these SDEs of the collection of measures, empirical measures that are achievable by Lipschitz algorithms. It gives the algorithmic threshold in optimization and constraint satisfaction settings of the problem. And the hardness is based on this SDE that tracks the evolution of this empirical measure over time. And the algorithms are following this IAMP framework that has been developed by other authors. So I can mention one open problem, which is that the question of, so it's, I guess, well understood now that these algorithms are finding sort of solutions that are atypical in that they live in dense clusters. And, but you could ask, like, what is the hardness, for example, of finding isolated solutions, since it's known that in many cases the typical solutions are isolated. Okay, and thanks for your attention and congratulations.